Adam Harper from University of Warwick, and he's going to tell us about large fluctuations of random multiplicative functions. Over to you, Adam.
Great, thank you very much. And thank you to the organisers for inviting me to speak here. I'm very pleased to be able to do it and to have just had a little bit of nice mathematical discussion, even remotely. So some people have seen me give this talk before. I apologise to them. It'll probably be very boring, but I hope that for people who haven't heard this talk before, it won't be so boring. So the plan is that first there'll be an introduction. I'll tell you what random multiplicative functions are and some of the things we know about them. And I'll state a new result. And then I'll say something about the proof. Depending on how the time goes, I might say more or less about that. But I'll give some idea of some of the ideas involved. And then at the end of the talk, I'll make a couple of remarks. And most of the talk has quite a probabilistic flavour. So if you don't like that, if you wait to the end, there are some things that aren't probabilistic at the end. So to motivate this, I want to talk about the Möbius function a bit, which is something that many people will be familiar with, but maybe not everybody so much. So what is the Möbius function? It's a function defined on natural numbers. And you define it to be 0 if the natural number has any repeated prime factors. And if n doesn't have any repeated prime factors, then it's just 1 or minus 1, depending on the parity of the number of prime factors of that. So, for example, mu of 1 and mu of 6 are both 1 because 1 has 0 prime factors and 6 has 2 prime factors, and they're all distinct. And mu of 2 and so on is minus 1. Mu of any prime is minus 1. And mu of 4 is 0 because 4 has a non-trivial square factor. It's divisible by 2 squared. And the kind of major property of the Möbius function is that it's multiplicative, by which I mean that mu of n times m is equal to mu of n times mu of m, provided n and m are coprime. And you can see this just from the definition, because if n and m are coprime, then when you take n and m, you just concatenate the prime factorizations of n and of m. So the condition of not having any repeated prime factors just splits up as a separate condition on the prime factors of n and of m. And the total number of prime factors, where you just add up the total number of prime factors of n and of m to get the number of prime factors of n and m. So the parity thing works out. So this is a nice kind of multiplicative function that takes the values 1 and minus 1 and 0 sometimes. And it's really interesting. It's very highly studied. And the reason for that is because it's closely connected to the Riemann-Zeta function and through the Riemann-Zeta function to the distribution of primes. And I want to say why, if you haven't seen this before. So if you give yourself some complex number s with real part strictly bigger than 1, you can form the Dirichlet series whose coefficients are mu. And this converges absolutely when the real part of s is strictly bigger than 1. You can multiply this by the Riemann-Zeta function. And if the real part of s is strictly bigger than 1, the Riemann-Zeta function is given by an Euler product, the product of the primes, this. And you can show that the Dirichlet series with coefficients mu is also given by an Euler product. It's given by this product of a primes. And at least if you don't worry about convergence, this is easy to check, because if you expand out the product over primes, what do you get? Well, you can get product of any powers of primes that you want in the denominator here, these p to the s factors. But you can only get one copy of every prime, because I only have 1 over p to the s in every bracket here. So I can only get square free numbers n in the denominator here. I can't get p squared factors, for example. And the coefficient I get is I get minus 1 multiplied together once for every prime factor of the number. And that's exactly mu of n. So this is the Riemann-Zeta function, this Euler product. This Euler product is this Dirichlet series of coefficients mu. And the point is that the factors here exactly cancel with the factors here. So this whole thing is just 1. And what that means is if you're interested in small values or zeros of the Riemann-Zeta function, so the Zeta function doesn't actually have any zeros with real part bigger than 1, but let's say small values, then because of this identity, because zeta times this other Dirichlet series has to equal 1, if zeta is getting really small, then this Dirichlet series with coefficients mu must be getting very large. So small values or sort of zeros of zeta correspond to large values or poles of this Dirichlet series. Understanding when they occur is equivalent to understanding the partial sums of the Möbius function. So this is a reason that the Möbius function is really interesting. I'll say some more about it in a little while. Now, in the 40s, Winkner wanted to try to understand how the Möbius function might behave. And to do this, he wanted to introduce a random model for the Möbius function, which would copy some of its important properties. And in particular, he wanted to copy the multiplicativity property that the Möbius function has. So this property here. And this thing that he introduced to do this is now called a Rademacher random multiplicative function. So this is the main topic of this talk. So I want to try to explain how his construction works. Coin tosses. These are called Rademacher random variables, these kind of plus or minus one random variables sometimes. And these gave the values of his function that he was constructing on the primes. So the value f of p for p prime was just this sequence of independent plus or minus one random variables. And then you want to extend this to a function on all the natural numbers. And he did that by saying that f of n should be 0 if n is not square free. And if n is square free, then f of n should just be the product of f of p for all the primes p that divide n. So this defines this random object on all natural numbers. And if you look at some of the properties, this is indeed multiplicative. So f of nm is equal to f of n times f of n whenever n and m are co-prime, just like for the Möbius function. And the reason this holds is just like for the Möbius function. So if n and m are co-prime, then to get the prime factorization of nm, you just concatenate together the prime factorizations of n and of m, and they don't interact. So the square freeness condition just splits up as a separate square freeness condition on n and on m. And if they are square free, well, f of nm is just the product for the primes dividing n times the product for the primes dividing m, which are all different primes. And that's f of n, f of n. And just by construction, f of n is equal to 0, like the Möbius function, if n has non-trivial square factors. And if n is square free, so if it doesn't have any non-trivial square factors, then f of n takes the values plus or minus 1, depending on the values of these underlying f of p. And so does. So f looks maybe a bit like the Möbius function. It takes the same set of values, although it takes them in different places, and it has this multiplicative. And so Winkner's idea was to study this random object to try to give maybe some insight into how the Möbius function itself was behaving. Now, there is another kind of random multiplicative function which I'll briefly mention. For the purpose of this talk, you can just think about this Rademacher case, if you like, this definition 1. But this second kind of random multiplicative function is actually more useful these days, I would say, and will be relevant to the thing I'll say at the very end. So these are called Steinerhaus random multiplicative functions. And the way you get them is now on the primes, you define your function to be an independent sequence of random variables, but now uniform on the unit circle instead of plus or minus 1. So uniform on the complex numbers with absolute value 1. And to make this into a function on all the natural numbers, you now don't worry about any square freeness condition anymore. You just say that for all natural numbers, f of n should be the product of f of p to the power a, where p to the a is the highest power of p that divides n. So whatever the prime factorization of n is, you define f of n to be the product of copies of f of p's corresponding to the prime factorization. And this gives you a random complex valued multiplicative function. It has this property. So f of mn is equal to f of m, f of n, now for all m and n. Actually, because of the way this is defined, you don't need any coprimality condition. And whereas the Rademacher random multiplicative functions were supposed maybe to be modeling the Möbius function, these Steinerhaus random multiplicative functions, they're supposed to model complex Dirichlet characters, so non-real Dirichlet characters, or functions like this, functions like n to the minus it for fixed real. And the key thing to note here, if you've maybe got a bit lost with some of the details of the definition, is that these values f of n are not all independent of one another. So some of them are. So on the primes, they're independent because that's how they've been constructed. But if you look at the sequence of f of n for all the natural numbers, they're definitely not. So for example, f of 6 is just equal to f of 2 times f of 3 by definition. So if we know f of 2 and we know f of 3, we exactly know f of 6. So this sequence of random variables f of n, they're not all independent. And that means that kind of classical probabilistic techniques will not tell us very much about the behavior of f of n, at least applied in the kind of standard way. So maybe this would be a good point to ask, are there any questions about what I've said up to here? If anything's not clear, please ask. Okay. Right. So I said earlier that there was a kind of connection between the behavior of partial sums of the Möbius function and small values or zeros of the Riemann zeta function. And this is part of the connection. So it's conjectured that the partial sums of mu of n up to x. So this sum in principle could have size about x because it's a sum of things that usually have absolute value 1. And it's a sum of about x of them. But it's conjectured that this should be much smaller than that. There should be a lot of cancellation between the plus and minus 1 signs. So it's conjectured that this sum should be of size big O x to the half plus epsilon for any fixed positive epsilon. And the truth of this conjecture is equivalent to the Riemann processes. So proving good bounds for partial sums of mu is very interesting and presumably also very difficult because of this connection. And what Winkler wanted to do was to look at his random model. So take his Rademacher random multiplicative functions and sum them up and think about how this behaves and see if that will give me any insight into what might be happening for mu. And since this is a random sum, we have to think about what kind of bounds we might get. And what Winkler specifically wanted was bounds that hold with probability 1, which are called almost sure bounds. So he wanted to know with probability 1, how big would these sums be? And the thing he had in mind, and that he mentions specifically in his paper, is this very nice classical probabilistic result, the law of the iterated logarithm. So what this says is that if you take a sequence of independent plus or minus 1 coin tosses with probability half each, but now completely independent, so there's no multiplicative structure here, it's just an independent random sequence, then almost surely the partial sums of this, the lim sup of these partial sums divided by square root 2x log x is 1. And also almost surely, so with probability 1, the lim inf, the same thing is minus 1. So with probability 1, the partial sums get out as big as square root 2x log x sometimes, so along some infinite sequence of x. And they get as small as negative square root 2x log x along some infinite sequence of x. And they don't get more positive or more negative than that, almost surely. And something just to note here is that if you just fix an x, look at the behavior of this partial sum, well, this is a sum of a lot of independent random variables. So by the central limit theorem, this should be behaving like a Gaussian with mean 0, because they all have mean 0 and variance about x. And the Gaussian random variable with mean 0 and variance x usually has size like a square root x, like its standard deviation. And here we're renormalizing by something which is bigger than that, something which is like root x log x. So this law of the iterated logarithm, this theorem, it says that when you look at all the values of x taken together, you get sort of bigger fluctuations than you would expect. You just situate yourself at a single point. So this result doesn't just say something about the distribution of the sum of individual x, it says something about how they all piece together. So it's quite an interesting and deep result for that reason. And what Winkler wanted, ideally, was some kind of statement like this, but for his random multiplicative object, which has a number theoretic structure. So I want to go through quickly some of what was proved about this partial sum of a random multiplicative function. So Winkler himself proved that partial sum is big O of x to the half plus epsilon, almost surely for all epsilon. And it's almost surely not big O of x to the half minus epsilon. So with probability 1, it doesn't get bigger than x to the half plus epsilon, and it does get bigger than x to the half minus epsilon along some infinite sequence. And this big O bound here, if we could prove this for the Möbius function, remember this would prove the Riemann hypothesis. So he proved that almost surely sums of these random multiplicative functions satisfy the equivalent of the Riemann hypothesis. And then this was improved in some unpublished work, Burdish. So he proved that the partial sums are big O of root x times some power of log, and they're not big O of root x divided by some power of a log, almost surely. And this was improved again in a very nice paper of Hollasch in the 80s. So this is a bit difficult maybe to pass if you haven't seen this before, but basically, so root x times a power of log is root x times e to some constant times log x. If you write log to the power ax as e to the a log x. And what Hollasch proved essentially is that instead of having e to the a log x, you could have e to the a square root log x in the upper bound. And similarly, you could have e to the minus some constant square root log x in the lower bound. So we put a square root into the exponents. And there are lots of nice ideas in this paper, which, for the sake of time, I don't think I'll get into trying to describe them all now. But this is well worth a read. And then most recently, the upper bound was improved by Pascal and by Lau, Tenenbaum, and Wu. So they proved that almost surely these partial sums are big O of root x times about log x squared. Root x times log x to the 2 plus epsilon, only fixed epsilon. And I improved the lower bound. So I proved that almost surely the sums are not big O of root x divided by power of log, divided by log x to about the power 5 over 3. And something I would say, I don't want to get into the details of what Hollasch did here, but these later papers here are sort of building on the basic method of Hollasch. So what I did uses the same kind of strategy for getting lower bounds that Hollasch used, but introduces some tools from Gaussian processors to make it more efficient. And similarly, what Pascal, Lau, Tenenbaum, Wu do to improve the upper bound follows the same kind of basic strategy as Hollasch, but with a kind of clever splitting device, which makes the moment bounds that he uses work much better. But all the kind of strategy of these arguments, the underlying strategy goes back to this Hollasch paper. Now, in this talk, I want to concentrate on the lower bounds. So let's just look at the lower bounds that I've written here and note that all of these lower bounds are functions which are smaller, which are slower growing than square root x. So this is square root x divided by a small power divided by x to the epsilon. This is square root x divided by power of log. This is square root x divided by power of log. So all of these bounds here are consistent with the fact that the partial sums of the random multiplicative function could always, almost surely, grow slower than square root x. And that's a very strange situation, which we wouldn't usually expect to see. But there's no reason a priori that that couldn't happen. Let me just say as well, I don't know if somebody's asking a question in the chat. If they are, I can't see it. But if you have a question, please just unmute yourself and shout, and I'll try and answer. So Hollasch asked us a question, is it true that the partial sums of the random multiplicative function should be big O root x almost surely? So is it true that actually the growth is only as big as square root x, the fluctuations only as large as square root x almost surely? And he happened to ask this in the Steinerhaus case, but I don't think there's any reason we'd expect the answer to be different if you look at the Rademacher case. And on the other hand, Erdős conjectured in the Rademacher case, but again, I don't think we'd expect there to be a difference, that this shouldn't be true. So he conjectured that the partial sum should not be big O over root x, almost sure. And he also said in this paper where he made this conjecture that so far as he knew, nobody had a plausible guess for the real almost sure size. So nobody had a guess for what would be the real analog of the full reiterated logarithm in this random multiplicative. Okay, so the result I want to say something about today addresses these things. So it answers this question of Polash, and it proves this conjecture. So this is the theorem. So if f of n is either of the kinds of random multiplicative function that I've been talking about, but you can just think of the random ACCA, the real case. And v of x is any function that tends to infinity, however slowly. Then almost surely, so with probability 1, there'll be arbitrarily large x, for which the partial sums are bigger than root x times log x to the 1/4 divided by v of x. So in particular, you could take v of x here to be something like log x to the power 1/100, say. And then the thing on the right-hand side would be root x times a positive power of log of x. So it'd be something that grows appreciably faster than root. So this shows that the sums are not big over root x almost surely, they get bigger than that. And as I'll explain at the end, I still think it's true to say that nobody has a plausible guess for the kind of real order of magnitude, so up to constants of this sum, at least I don't. But I think it's plausible that this exponent 1/4 is the correct exponent in this problem. And at the end, I'll say why. So what I want to do next is try to explain how the classical law of iterated logarithm, so this statement here, just for completely independent random variables, is proved, or a way of proving it. And then once I've done that, I want to try to explain how you can adapt that strategy to the random multiplicative case. But before I do that, are there any questions about the statement of the theorem, or any other questions up to this point?
So does that indicate that for the Möbius function, this log x to 1/4 should be the truth?
I would say not. Okay. So I think for the Möbius function, there's an alternative conjecture based on a random theory, which would be root x log x to the 5/4. That's right. And
I remember now. Yes.
Yeah, and in my view, that's much more plausible for Möbius. But what I'll say at the end is that this probably does suggest what should happen for partial sum characteristics. I think it's a good model for that case. It's not actually a good model for the Möbius function.
So can you remind me the two kinds of random multiplicative functions?
Yeah. So the Steinerhaus one is the one that takes values on the unit circle. So it's supposed to be modeling complex Dirichlet characters.
I see. The other one is ±1.
Yes.
Okay. Thank you.
Okay. Any other questions or comments? Okay. If not, so let me try and talk about the lower bound part of the classical Fourier algorithm. So by that I mean proving that there are large fluctuations, the partial sum of the sequence of independent random variables. The way I'm going to do this is certainly not kind of novel to people who think about this a lot, but it's probably not the way you'll have seen this proof done if you've seen a kind of first course of probability that handles the law of and I'm presenting it this way because this will generalize better to the random multiplicative case. So I claim that it will suffice to prove that if you take your partial sums of your independent plus of 1 times and you rescale them in the natural way, like standard deviation, and you take the maximum over some interval, let's say between capital X to the 8/7 and capital X to the 4/3, but it doesn't really matter, just some fairly big interval. It will suffice to prove that the maximum of this is bigger than about root 2 log x, with probability tending to 1 as capital X is here, tends to infinity. And why will that suffice? Well, if the maximum is bigger than this, with probability tending to 1, that means the complementary thing, the maximum being smaller than this, will happen with probability below 1, so probability tending to 0. And if that's true, then we can find a sparse sequence of values capital X, depending on how quickly this little o1 goes to 0. So that along that sparse sequence of capital X, these failure probabilities are like, let's say, 1 over the squares, like the reciprocal of the squares. And then if we sum up those failure probabilities along that sparse sequence of capital X, it will converge, because the sum of 1 over the squares converges. And then there's a nice and actually very easy to prove result from probability theory called the first Bell-Cantelli lemma. And that tells you that if you have a sequence of events and the sums of all their probabilities converge, then with probability 1, only finitely many of those events will occur. And remember that these events we're talking about here are the failure events, the complement of this. So the first Bell-Cantelli lemma will tell us that almost surely only finitely many of these failure events will occur along this sparse sequence of X values. And that's another way of saying that from some point onwards, along this sparse sequence of capital X values, this will always hold its success event. And the difference between this way of talking about the proof, this is just kind of the start of the proof, but the difference between this structure of the proof and what you might have seen before is that here I'm using the first Bell-Cantelli lemma, and often you would use the second Bell-Cantelli lemma for this existence of large fluctuations part. But the second Bell-Cantelli lemma requires that the events that you're working with are independent. And that's a big problem for random multiplicative functions. We'll never be able to engineer things for random multiplicative functions so that our events are exactly independent. Whereas the first Bell-Cantelli lemma doesn't require any independence assumptions. It just requires that the sum of the probabilities of the events converges. But the price you pay for that is that to get the sums of these probabilities to converge, you need to know this lower bound occurs with probability tending to 1. If you're able to use the second Bell-Cantelli lemma, you just need these probabilities to be not too small. I won't get into that, but if you've seen a proof of this using the second Bell-Cantelli lemma, you'll understand what I mean. So what we've done here is to move some of the kind of difficulty about. So you don't need to know independence of these events anymore, but you do need to know that they occur with probability tending to 1. So what I want to explain is how you can prove that happens, how you can prove this does hold with probability tending to 1. So if you just fix an X, this rescaled sum by the central limit theorem has a roughly Gaussian distribution, a roughly normal mod 1 distribution. And we know everything about a single Gaussian random variable. But what we have here is the maximum of a bunch of these random variables corresponding to different little x. So we need to understand the relationship between these sums as little x as the endpoint variance. We need to understand the dependence between these sums. And the great thing about Gaussian random variables, which is a thing I always try to emphasize in these probabilistic number theory talks, and if you don't take anything else away, I hope you'll take this away from what I'm saying, is that the Gaussian random variables, to understand the dependent structure, you only need to understand the means and the variances and the covariances. And that's absolutely not true for general kinds of random variables. But for Gaussians, for jointly Gaussian random variables, that's all the information you require, in principle at least. So here we understand the means and the variances. These have mean 0 and they have variance 1. So to understand the dependence, we need to understand the covariance or the correlations. And that means the expectation of the product of this sum for different x and y. And actually, it's pretty easy to see what this will be. So there's a factor square root x and square root y that comes out here. And then when you take the expectation of the product of the two sums, because the epsilon n's are independent of one another, the only terms that survive are the ones that occur in both sums. So that's the ones that go up to the minimum of x and y. So this covariance will be the minimum of x and y divided by square root x, y. And you can see that that's at most 1, which is good. It's a kind of sanity check because it has to be at most as big as the variance, which is 1 from up here. And if you decide just to look at points of the special form of powers of lambda, for some fixed lambda bigger than 1, let's say, so look at some kind of geometric sequence points. Well then, so if x and y are of this form and they're not the same point, then whichever one of them is bigger must be at least lambda times as big as the smaller one. I have two different points in the sequence. So that means that the thing in the denominator here, so the bigger one of these will be at least lambda times as big as the smaller one. So that means the denominator here will be at least square root lambda times as big as the numerator. So along this sequence, for all different points x, y, we're getting upper bound for this covariance, which is like 1 over square root lambda. So if lambda is large, this is getting small, and that's sort of getting closer to the situation of these things being independent. So kind of the smaller the covariances, the more independent the random variables, the random sums are. Now, we're interested in the maximum here over this interval. So how many of these kinds of points can we actually fit into this interval? Well, it's log of this end point divided by log lambda minus log of this other end point divided by lambda, essentially. And that's some constant times log x over log lambda. Okay, so if you look at just values of x of this form, we can have about this many of them in this interval, and we have this, this kind of understanding of their covariance structure. And then, as I said, for Gaussian random variables, if we know their covariances, we know an awful lot about how they behave. So, for example, if I have some standard normal random variables, so some Gaussian mean zero variance one random variables, and I know that all their correlations for I not equal to j are bounded above by rho, where rho is some fixed thing strictly less than 1, then you can prove that the maximum of these Gaussians will be bigger than about square root 2 1 minus rho log n, with probability tending to 1 as the number of random variables tends to. So if rho was 0 here, so the correlations were at most 0, that would essentially correspond to the GI being independent of one another. And then it's quite a well-known fact that the maximum of n independent standard Gaussians has size like square root 2 log n with very high probability. And this is a generalization of that, the case where these aren't independent, you just have this kind of control on their correlations. So if we look back at the setup here, so the upper bound we had for the covariances was 1 over root lambda. So we could take rho to be 1 over root lambda. And the number of tries we have, the number of Gaussians, was this thing here. And if you plug all that in, where you get square root 2, you get 1 minus rho is 1 minus 1 over root lambda. And log of this, well, it's basically log x. There's a small amount of dependence on lambda from the denominator here, but I've just kind of put that in the below 1 here. And lambda here could be anything. So if we take lambda arbitrarily large, we can make this as close as we want to square root 2 log x, which is what we're trying to prove. So this is a proof of the lower bound part, the existence of large fluctuations for the classical law of the expected value. And let me say that what I've shown you here is basically a real proof. So I didn't actually show you the proof of this fact, but it's not too difficult. And I didn't actually show you a proper statement of the central limit theorem that would suffice to treat all these things as Gaussians, but that also can certainly be done. And everything else I showed you here is correct. So there aren't any really lies in this proof. And the key thing that made this work was that for Gaussians, we just need to understand the covariance structure to understand, for example, how large the maximum will be. And we could compute the covariances. So can we do something like this for random multiplicative functions? So this is going away from the strategy that Hollash introduced in his paper, which I haven't actually explained to you how it worked, and going back to something more like the classical probabilistic approach, proving the existence of large fluctuations. So can we do this for random multiplicative functions? Well, of course, the answer is yes, because otherwise I wouldn't just spend that time telling you about it. But there are some significant issues. The biggest one is that if you look at the partial sums of the random multiplicative function and you rescale in the obvious way, by the standard deviation, this does not have a roughly Gaussian distribution. Remember before, when we were just looking at sums of completely independent things, this was roughly Gaussian. It's not in the random multiplicative case. That's not obvious, but it's true. And in fact, if you rescale in this way by square root x, this thing will usually have size like 1 over log of x to the 1/4. That's something I proved a few years ago, but it was published last year. So if you rescale in this way, this thing will actually be tending to 0 probability. It will have size that's usually quite small. And even if you change the rescaling here to take account of this, this still won't have a roughly Gaussian distribution. And everything I said about just needing to understand the covariance structure to understand the maximum was for Gaussian random variables. So this is a real issue, but we can get around it. I want to try to explain how. So I think I'll talk about this for maybe 5 to 10 minutes, and then I'll give my 2 closing remarks, and then I'll finish. So as before, it will suffice, I claim, to prove theorem 1, the lower bound for the sums of a random multiplicative function, to show that if you look at the maximum of these partial sums, we scaled root x over some big interval, let's say between capital X to the 8/7 and capital X to the 4/3. This will be bigger than log x to 1/4 over v of x, with probability tending to 1. So we don't have root 2 log x here anymore. We have the thing that we're shooting for in theorem 1, log x to 1/4 divided by this function v that's tending to infinity. But apart from that, this is exactly the same as the start of the proof that I showed you for the law of iterative logarithm. And the reason this suffices is exactly the same as in that case by the first Bell-Contelling lemma. And I claim that actually it will suffice to prove something like this, not for the complete sum here, but just for the sum over numbers with a fairly big prime factor. So the sum over numbers with a prime factor bigger than capital X, where capital X is the parameter. And also you can take the real part here if you want. So if you're thinking of f as a Rademacher random multiplicative function, it's real valued anyway, so this is redundant. But in the Steinerhaus case, it's a bit convenient here to take the real part rather than working with the whole complex value itself. So why does it suffice to do this? Well, certainly if you can show the existence of a large real part, then you have the existence of a large absolute value. Why does it suffice to work with just this subsum over the numbers with a big prime factor? Well, the idea is that for any given little x, it'll be quite rare to have a large value of this sum. So it'll be quite rare for this thing to be large. It will also be quite rare for the corresponding bit of the sum over the numbers with all their prime factors less than capital X to be large. So the probability of both of these things being large together and sort of cancelling out will be very small. So if we can show the existence of large fluctuations of this, it's very unlikely that at the same points where this gets large, the other bit of the sum will be large and pointing the other way and cancel out. And actually, it's pretty easy if you set up the argument properly to make that rigorous. So that's why it's okay to restrict to these numbers with a big prime factor. Just note that little x starts at capital X to the 8/7. So there's a positive proportion of terms in this sum that have a prime factor that's big. So we shouldn't have lost too much by restricting to. And the advantage of looking at this is that numbers less than x, which have a prime factor bigger than capital X, they only have one because they're not big enough to have 2 prime factors of this size. And then by multiplicativity, we can split up the sum in terms of this big prime factor, so the prime factor they have, which is bigger than capital X, f of p, and then the rest of the number. So f of m for the part that's less than x. So it will suffice to show that the corresponding statement, but for this. So it will suffice to show the existence of large fluctuations of these sums. Now, I said before that these sums of random multiplicative functions don't have roughly Gaussian distributions. This sum doesn't have a roughly Gaussian distribution either. So that's an important thing to emphasize. It's not correct to think of it as having a roughly Gaussian distribution. It has a very different looking distribution with much fatter tails. But if you look at this, so we have these independent random variables f of p, and we have these sums of f of m. And the primes that occur here are all very big, and the numbers m in these inner sums are all relatively small because they're little x divided by these large values of p. So there isn't actually any overlap between the f of p's that occur here and the f of p's involved in these inner sums. So these coefficients f of p are independent of all these inner sums. So what that means is if you kind of freeze all the randomness coming from these inner sums, it doesn't affect the randomness in the f of p's because they're independent. So if you condition on these inner sums, then what this looks like is a sum of some independent random variables times some coefficients. And that's the kind of thing that you would expect to have a Gaussian distribution. And it does. So if you condition on this huge amount of information, so you freeze this huge amount of randomness in the inner sums, then conditionally, these sums do have Gaussian value. Conditional Gaussian value. You can use a multivariate central limit theorem to do this precisely. It's not so difficult. But it's important to emphasize here, there's a huge amount of information that's being extracted out. There's a huge amount of conditioning that's being performed to make this true. So just the sum individually certainly does not have a roughly Gaussian distribution. But if you condition a lot, the conditional thing will have a roughly Gaussian distribution. So now we can try to do, now we've got to something that looks Gaussian, we can try to do again what we did for the classical reiterated logarithm by analyzing the covariance structure. But now it's not the mean and the variance and the covariance, it's the conditional mean and the conditional variance and the conditional covariance that needs to be understood. So we need to understand, once we've frozen all this stuff, what do the means and the variances and the covariances look like then? Now the means are easy because the f of p is independent of all this stuff that's been conditioned on, and they all have mean 0. So the conditional mean is still just 0, so that's good. The conditional variance is not so easy to understand, but fortunately it's something that basically already arose in the in this work, showing that these sums usually have size like this. So you can show that the conditional variance here is something like the integral of the Euler product that corresponds to the random multiplicative function. So the product over primes up to capital X that corresponds to the random multiplicative function squared over this little interval rescaled. This isn't obvious at all, but this is something that was sort of known because of this previous work. And if you look at how this behaves, so this depends on the f of p for the small prime of p, this depends on the conditioning. But you can show that with probability tending to 1, this will be bigger than 1 over v of x squared, this slowly growing function, times root log of x. So let me note here, you need this function v of x at this step to get this probability to tend to 1. So you could show that this was greater than 1 over root log of x with some positive probability. If you want the probability to tend to 1, which we need for the overall argument, you need to put this factor in here that's tending to 1. So this is where v of x comes in the argument. And this root log of x here, well, this is a bound for the conditional variance. So if you take square roots here, you get a bound for the conditional standard deviation. If you take the square root of this, you'll get like a 1 over log of x to 1 quarter. And that's the same 1 over log of x to 1 quarter that's here. So in the classical case of the sums of the completely independent epsilon n's, the variance has turned out to be 1 because the typical size of the point was like square root x, just like the scaling factor. Here, the conditional variances turn out usually to be like 1 over root log of x, so the conditional standard deviations turn out to be like 1 over log of x to 1 quarter, because the typical size of a point is not square root x, it's like square root x divided by log of x to 1 quarter. So that's where the log of x to 1 quarter comes from. And now, to finish, we need to understand the covariance structure. So the conditional covariance between the sums at different points, so for little x and the y, it turns out to be something very roughly like this. So it's the same kind of integral, but with a factor x over y to the minus it inside it. So if x is equal to y, so if we're at the same point, so we're looking at the variance, then this is just 1, so it's the same thing as up there. But if x is away from y, then x over y is something that's not 1, and this will rotate as little t varies over this interval, or you might hope to get some cancellation from this factor x over y to the minus I. And what we want is we want the conditional covariances to usually be appreciably smaller than this lower bound we have for the conditional variances. So before, when the variances were 1, we wanted the covariances to be smaller than this small number rho, let's say. So now the conditional variances are like this. So we want the conditional variances to be appreciably smaller than this if we want to get independent behavior. And you can show with quite a lot of work that with probability tending to 1 over the realizations of this random product, that will be true for a lot of pairs x, y. You can't do it for all of them, at least I don't know how to, but you can show that there'll be a lot of these points x, y if they're well spaced out, where this integral here will be a lot smaller than this, where this extra factor here gives you a lot of cancellation. And that means that this space sequence of points neglects, the corresponding conditional Gaussians are behaving roughly independently. And then you can conclude the argument as before. So let me, won't really say anything about how you do this covariance calculation, which is the main sort of technical thing in the proof. It uses some kind of standard analytic number theory tricks for such things. So you look at the sum over different points of a big power of the integral that you're looking at, and you try to get some cancellation in that. You expand everything out, but actually doing it is rather delicate. So there are big contributions to these integrals from just little ranges of t, and you have to understand their structure quite well to make the argument work. So if anybody's interested, they can maybe ask about that. But to finish the talk in time, I just want to make these 2 final remarks that I promised. So I say at the start that maybe this exponent 1/4 in theorem 1 was sharp. Why might that be? Well, in the classical law of reiterated logarithm, you get size square root x times square root log of x. You get an exponent 1/2 here. Why is that? Well, that's because at a fixed point x, the typical size is like root x. And then taking the lim sup multiplies that by a factor root log of x. You look along a kind of space sequence of points. In the random multiplicative case, the typical size of a point is not root x, it's root x divided by log of x to 1/4. And the lower bound we had in the almost sure theorem in theorem 1 is again this thing multiplied by root log of x. So the relationship between the behavior at a point and the lim sup behavior is the same in the theorem in the random multiplicative case in theorem 1 as in the classical case. The answer is just different because the typical size of a point is different by this factor log of x. So this is a reason to believe that this exponent 1/4 might be sharp. It's far from being a proof of that, though. So there are a lot of issues in trying to get a matching upper bound. We don't have one at the moment. But I would cautiously guess that this exponent 1/4 is the correct thing for the partial sums of a random multiplicative function. So we also promised I'd say something non-probabilistic at the end for people who have been hanging around hoping for that. So instead of looking at the sums of a random multiplicative function, you could look at the sums of a deterministic multiplicative function like a Dirichlet character. So you could look at the partial sums of some Dirichlet character chi of n, rescaled by root x. And you could ask how large this gets in some interval. So this is supposed to be an analog of the thing we had in the treatment of random multiplicative functions. So here you take a random multiplicative function, you rescale it by square root x, by the standard deviation, look at the maximum in an interval. So a kind of deterministic analog of that would be to take the partial sum of a Dirichlet character, rescale it, and look at the maximum. And in the random multiplicative case, we could say something about how large this gets with probability tending to 1. So that would be equivalent to saying something about how big this maximum gets for most Dirichlet characters. So let's say for 99% of Dirichlet characters, modulo some large. So theorem 1 would suggest, and I would believe this, that provided capital X, the length of the interval, isn't too close to the R. So let's say provided capital X is at most R to the 3/4, so that capital X to the 4/3 is at most R, then the maximum of this rescaled thing should be like log of X to 1/4. For most characters, for 99% of characters. So a lot of work has been done on partial sums of Dirichlet characters on their maximum size, but usually when we talk about the maximum, you mean the maximum over characters. So you try to find some peculiar characters where you get large values. And that's not what I'm asking here. So I'm asking what happens for most characters just by varying the endpoint of the sum. And this is a problem that I think hasn't really been studied before. So I would conjecture that this should be true. So for 99% of Dirichlet characters modulo some large prime, the sum should get as big as log x to 1/4 times the obvious guess, the standard deviation. So the questions here are, what can be proved rigorously? You should be able to get something for some range of little x just by mimicking the proof from the random case, but you certainly couldn't, by any obvious modification of that proof, do the case where little x is, let's say, r to the power 0.1. I would still expect this to be true, but there's no obvious method to attack that. Even proving something weaker than this would be interesting because, as I say, I don't think anything's really known about this problem. And also what happens for larger capital X. So when capital X starts to get closer to the conductor R, we know the answer must change. I won't go into that. Again, if people are interested, they can ask. So how does it change? What's the transition that happens when capital X gets larger and larger? Okay, so I hope some people found that question interesting, maybe, and found the rest of the talk interesting. And that's all I want to say. So thank you very much.
Thank you, Adam, for this beautiful and really clear talk. So are there questions from the audience? Yes, sir. Please go on.
Hi, okay, I'll talk. It's
Sure.
Andrew here. So I guess these last couple of slides, you're assuming that you're going to have a root log x law. It's just that kind of your floor that you're working from is root x over log x to the quarter.
Yes.
Do you have any idea what the probability distribution is at root x over log x to the quarter times some function?
Yeah, so it should be a probability distribution that comes from, so use some buzzwords now. So it comes from the total mass of critical multiplicative tails. So in particular, that means that the tails are much heavier than a Gaussian. So the probability that the sum is bigger than lambda times root x log x to 1/4 should be something like 1 over lambda squared on a big range of lambda.
Okay, and this is consistent to your conjecture of.
Yeah, I mean, this is why you get the blow up this is why the moments change behavior at the second moment, because of this lambda square.
Yeah, I guess intuitively, I just think if you've got a lot of, as you say, the tail doesn't decrease very fast, then your conjectures may be risky, but you thought this.
Yeah, so right. So it's far from obvious that this is the right answer. The main thing is that, so to get the existence of large values, you just look at the part of a sum where there's a big prime factor. You don't have to worry about the part of a sum where there isn't a big prime factor. And to get upper bounds, you do need to worry about that bit of the sum. So it's possible there could be some kind of conspiracy in that bit related to the heavy tails that would spoil the upper bound. My feeling is not, but I think until we have a proof, I don't really know. There's going to be some kind of quite subtle interaction between the tail behavior at a single point and the dependence between the sums at different points. Need to understand.
Yeah, thank you.
Any other questions? Okay, so if not, let's thank the speaker again.